All right, welcome back to chemistry class. You guys, I'll tell you one thing. I really miss like actually teaching in the classroom. This is kind of a little bit difficult. I'm not completely used to it, but we are getting there. So I hope you guys are staying safe. Hope you guys are staying healthy. Um, Trying to get used to this whole teaching online thing. So we'll just keep going with it. So today, what I did is I put up. You guys probably saw already if you've been on the computer. You guys have probably been on and saw that I put a couple worksheets on there. I saw some people have already worked through some Khan Academy. That's awesome. Um, but last night I made a video where I was talking about binary ionic compounds, and I'm going to expand on that a little bit today, and I'm going to go into the next step, which is molecular compounds. So you're going to see that actually, quite honestly, molecular compounds are a little bit easier, and sometimes I think they're too easy. So I'm going to talk about the differences between the two. We're going to go through, just some of the ins and outs, the differences, how they're, how you can tell the difference between them, and then the rules for writing molecular compounds and for naming molecular compounds. So I actually, to make this online teaching thing a little bit, nicer for me, I have somebody here to help me. So come on in here.
Hi.
So, you guys have seen this kiddo around from time to time. So she absolutely wanted to be in the video. So, oh, and the little guy came over here too. This is Archer. You guys don't get to see him. But if any of you guys are working in the coop next year, you're going to get Archer.
Yep.
I apologize in advance for that one. Okay, so anyways, I put this PowerPoint up on the on Teams, so you can access this and you can just flip through it and just so you have access to the PowerPoint. And I went through a lot of this last night, so I want to flip through because there's a couple things I didn't really touch on, and some of the worksheets actually ask about them. So when we go through ionic formulas, I'm just going to flip through here. I didn't talk about the properties. So if we were going through this, like we need to take a test on it in a couple weeks, like we usually would, then I would go more into detail with this. You don't absolutely need to know this because you're not going to get tested on it, and quite honestly, it's not stuff that you end up having to like memorize down the road. It doesn't come up very often in chemistry. Typically the way it works is we end up having it on the Unit 4 test, and then you kind of forget about it the rest of the semester, and it's not something that you absolutely have to know for the long run of chemistry. Maybe if you went down the road a couple chemistry classes later, it might come up that you had to know the properties of ionic compounds. But anyways, generally they have high melting points, they have high boiling points. One of the biggest ones, especially like in this class, what they usually do, like on the Unit 4 test, they always test on knowing that ionic compounds conduct electricity and that they form strong electrolytes. So really that's all you would have to know. So when we talked about the properties of ionic compounds, that's what you would need to know. So on the worksheet, that's it. I'm going to need you to stay still because they're trying to see the screen, okay? All right, thank you. Okay, so the basic structure of ionic compounds is that they form what are called lattice work structure. So when we say something like salt is NaCl, which you guys have probably heard that before, it's sodium chloride. NaCl doesn't mean that there's one Na and one Cl. What it's telling you is that it's a ratio. There's one Na for every Cl. So a lot of times you'll hear the term salt crystal. It's because you have a big crystal of where you have a bunch of Nas and Cls, but they alternate 1 to 1. So if you had something else like magnesium chloride, which is MgCl2, what it's saying is it forms this big crystal where you have 1 Mg for every 2 chlorines. So it's just telling you a ratio. So if it's MgCl is 1 to 2, you might have 100 magnesiums, but 200 chlorines. It's actually much bigger numbers than that, but I'm just using that because those are numbers we're used to hearing. So it's just a ratio. That's all it's telling you. That's what an ionic compound is telling you when we write that formula. So NaCl just tells you have 1 sodium for every chlorine. So that's what's called an empirical formula gives us. Empirical formula, the term empirical actually means it's based on data. We would have done an empirical formula lab in class where we actually find an empirical formula of a compound. That would have come up next unit. We would have done that, and we can see how it goes. Maybe I'll in some way do some sort of a demonstration if I can find a way to do that without getting into the chemistry lab. I don't know. I'll have to try to be creative. But anyways, that's basically what it is. Empirical formulas, that's what you guys are doing right now. That means based on data, that's what empirical stands for. Now, the next slide is kind of what I was talking about. When we talk about ionic compounds, this is what's called a lattice work structure. As you can tell, like the green is a negative, that would be an anion, and it's surrounded by positives. So, but if you count it all the way through, you have 1 negative, 1 positive, 1 negative, 1 positive, 1 negative, 1 positive, 1 negative, 1 positive. It's a 1 to 1 ratio. So that's something like sodium chloride. Or it could be potassium chloride, or or sodium bromide, whatever, anything that's a 1-to-1 would form this kind of a structure. And this is like a cross section of, like, this is supposed to be like more 3D, but you can still see it's how it's alternates, so it's a 1-to-1. And that's what's happening with those crystal structures. So that's what ionic compounds do. I kind of went through this yesterday. You balance your charges when you do your ionic formulas. Watch the video of ionics, and I went into this in a lot more detail and how we do that. We, talking about the transition metals, how you need your Roman numerals. You have to be careful with that. You have to recognize when you need a Roman numeral when you're naming those compounds. I went through this yesterday, so you guys can read through this, and you can again watch that video that I put up before. And then I wanted to go through this one too, the proper anion names, because I see this sometimes. A lot of times I will get a lot of students will ask me, how do you actually name these? How do you name, how do we name, is it oxygenide? No, it's oxide. So I kind of just put a list up here so you know how they're actually named. Or phosphoride is another really common one I see sometimes. So you need to make sure that you know what the proper anion names are when you're naming these particular compounds. So carbide, nitride, oxide, fluoride, phosphide, sulfide, chloride, arsenide, selenide, bromide, and iodide. And I think that's all we'd have to get to. Those are basically our nonmetals, the ones that form anions. Okay, now we're going to get into moleculars. And again, this is a continuation of the same PowerPoint. It's up on Teams, so you can access it. The molecular compounds are a little bit different. They have low melting points and they have low boiling points. So it's just the opposite. They don't conduct electricity. The ionic compounds, they conduct electricity a lot easier, especially when they're dissolved into water and whatnot. So here, when you dissolve a molecular compound into water, they form strong electrolytes, or they can form weak electrolytes. It just depends on the molecular compound. So they can form either one. Whereas ionics, they form strong electrolytes. So moleculars could be either one. Okay. Now, here's a big difference between molecular and ionic. The ionics, like I was just talking about, ionic compounds form that crystal structure. It's called a crystal lattice structure. Like I said, it's, when we hear about a salt crystal, it's because you have sodium, chlorine, sodium, chlorine, sodium, chlorine, sodium, chlorine, all the way through. You have all these sodium chlorines, like I showed you in that one slide earlier. When we're dealing with moleculars, they form molecules. So when we have, something like water, we don't have, we can get water crystals, but it's molecules that end up forming that crystal, not these atoms that are all stuck together. So when we have water, we have this H2O that goes like this, and then this is all one molecule right here, and then we might end up with another H2O down here, something like this, but these are all their own molecules. They don't form that crystal lattice structure. Whereas when we look at sodium chloride, we have Na, Cl, Cl, Na, and it just kind of goes all around like this, where it's all one big crystal all the way around, kind of like what I showed you on the picture from before, where these are separate molecules. So water would form molecules. Anything that's molecular forms molecules instead. They have their individual molecules. So we are going to talk about molecular formulas now. So and how they, molecular formula tells us exactly how many particles are in each, or how many atoms are in each molecular compound. So they look like this. Like this would be something that'd be a 1-to-1, but this is a molecule, this is a molecule, this is a molecule. That doesn't exist as one whole thing. Now, there are times, like I said, a water crystal, a crystal of water, we end up with these other intermolecular forces that are, that kind of these weird things happen that we're not even going to talk about, this whole different level of chemistry. But there are ways that you can get a water crystal where you get these different bonds that aren't actual chemical bonds that come to, that hold these things together, and it's just a little bit different that we're not gonna worry about. Okay, now when we write formulas and we want to name molecular compounds, this is quite honestly a lot easier than ionics. The reason, we don't have to worry about charges. And the reason for that is because moleculars are always between two nonmetals. Ionic compounds are always between a metal and a nonmetal. If I was giving this lecture in class, I would say, write that down. That's super important. You absolutely have to know the difference between how to recognize the difference between ionic and molecular. And I would say, okay, ionic, metal, non-metal. You guys would be repeating it, all that good stuff. So we make sure you guys know that. Difference between ionic and molecular. Ionic is between a metal and a non-metal. Molecular is two non-metals. So remember, metals left of the stair step, non-metals right of the stair step. So if both of the things are to the right of the stair step, then we know it's going to be two non-metals, and it's going to be a molecular compound. So that's what this says right here. First, make sure both elements are non-metals. Oops, I just slid that over. Formula writing. We got to use our prefix. If you look on the back of your periodic table, we're going to see at the bottom, I believe, it's going to give you these prefixes, and it's like mono, di, tri, and on and on and on. It gives it to you on the back of the periodic table. You'll see that. So what those prefixes tell you is it just tells you the number of atoms in that molecule. That's it. So for instance, right here, where it says formula, and the prefixes tell you the number of each atom. So if it says dinitrogen pentoxide, and you look on the back of your periodic table, di means 2. So that means it's going to be N2. Pent means 5. So it's going to be pentoxide. It's just going to be 5 oxygen. So you write N2O5. That's all you got to do. And then when you're naming, it just goes in reverse. So for naming, we just use the prefixes, and it just goes in reverse. So if I had H2O, the formal name for H2O would be dihydrogen, because you have 2 hydrogens, monoxide. So you just throw on that prefix. That's all you have to do. And then on the second atom, we would actually write an IDE like we did with our ionics. So again, remember, molecules are not ionic bonds. It doesn't have to do with ions. There's no ions here, so we don't have to worry about charges. There are no charges. That's one of the mistakes that I see. A lot of my students who try to do moleculars, and they're like, oh, well, this is a 2 negative and this is 3 negative, so they try to balance charges. You don't do that because they're not ions. They're sharing their valence electrons, not transferring valence electrons. So that's pretty important. You just simply look at the prefixes. Super, super easy. Here's our prefixes: mono, di, tri, tetra, penta, hexa, hepta, octa, nona, and deca. I believe, if I'm not mistaken, I don't have one of the district periodic tables with me left in my classroom because I didn't expect that we were going to be home for the rest of the semester. I think the periodic table you guys have doesn't have the 7 or the 9. Not that big a deal, but at least you have this in case that were to come up at some point. Not a big deal at all. Speaking of periodic tables, if you don't have your periodic table, if you left out school or you just don't have one, I'm going to get one. I'm going to scan it in. I'm going to find one of the periodic tables like we had in class. Luckily, I get to go to the school tomorrow, and I guess I get to wrap my classroom up and get it ready for the summer since I don't get to go back again after that. So one of the things I get to do is I'm going to grab one of the periodic tables and I'll upload it on Teams for you guys. Okay, that's what I have. I'm going to do a couple examples, so I'm going to get my kiddo out of the way here so I can use the board and say bye.
Bye-bye.
Okay. So I'm going to just do a couple of examples for you guys. So just so you know, just so I have examples. So if I had something like, I don't know, let's say I have this compound, that formula, I get N2O5. So is that the one I actually did? Now I'm thinking about it, I think that's the one I already did, N2O5. I did that on the previous page on the PowerPoint, so I'm not going to do N2O5. Let's say I have something else. Let's say I have, I know what I'm going to do. Let's say I have CCl4. That's carbon tetrachloride. That's carbon with 4 chlorines. So when I want to write that out as a formula, what I'm going to do is first I'm going to recognize that this is 2 nonmetals. So since it's 2 nonmetals, I know it's molecular. So I'm going to look at this one and go, I have 1 carbon. So I'm going to write mono, and I'm going to write carbon. And then I'm going to erase this for you real quick, 4 chlorines. So that's going to be tetra. And then it's chlorine. So I'm going to write chloride. So that would be one of my formulas. So monocarbon tetrachloride would be the formal way to write that. Now, what you can do, and you see this all the time, if the first element is a 1, you don't have to write the mono. But you would have to write mono if it was the second one. But that's one exception to the rule for molecular. So you can take this mono, and if it's not there, it just means 1. So that happens sometimes too. Here's another one. Let's say I had I'll do a simple one. You guys have all seen this one, CO2. You guys probably recognize that. Carbon dioxide, right? Carbon dioxide. Notice I didn't put the mono right there because that would be the first one, the first element. I mean, so that I don't write mono. If it's anything else, I would write the prefix. So if I had something like P2O5, that would be di. I do have to write the prefix now because it's not one. So diphosphorus. And then 5 would be pent, so I'd write pent oxide. So that's all I got to do when I want to name it. Now, if I have a 1 for the second one, like I used water for example, I have H2O. Now I have to write the dihydrogen. And then the second one, I do have to write the mon. So that tells me it's 1, monoxide. So dihydrogen monoxide would be the formal way. I know we didn't call it that, but that'd be the formal way to write it in water. So again, all we're doing is writing our prefixes. If you want to go backwards, then all you do is you just write the element with a prefix on it. So if I wanted to write the name of CCl4 or carbon tetrachloride, you just go, okay, well I have 1 carbon, so I'm going to write C1. Tetra means 4 chlorines, so Cl4. As simple as that. Carbon dioxide, 1 carbon, 2 oxygens. Like diphosphorus pentoxide, P2, because this di means 2, pent means 5, so it's O5. Dihydrogen monoxide, 2 hydrogens, 1 oxygen, H2O. And you just do it like so. And all the moleculars are just like that. There's no tricks to it. You don't have to worry about Roman numerals or anything like that. It's just as simple as that. If you recognize that it's molecular. Now what you can't do is start trying to do like ionic compounds like they're molecular compounds. Like if you see MgCl2, you can't go magnesium dichloride. That doesn't work because that's an ionic and not a molecular. Moleculars only get to use prefixes. So you have to be careful about that. Okay. What I'm uploading on Teams, I'm going to put a couple of worksheets up there. I have this PowerPoint up already, so you can look at the PowerPoint. I have another Poggle. I like those Poggles because they kind of walk you through and try to explain to you guys how to do these different these different formula writing processes. So go through the Poggle if you want to, and it just kind of helps you out. I put a couple of worksheets up that are pretty quick about just molecular formulas, and then I put one up that is a combo. It has molecular compounds and it has ionic compounds. So that way you have to identify the difference. So you have to look every single time. Is this ionic? Is it metal, non-metal? Or is it molecular? Is it non-metal, non-metal? So you have to be able to identify. So that's really important. So those are some good worksheets to go through. Continue going through the con if you feel like that's helping. I've noticed that some of you guys have already been going through that. A lot of you guys have gone quite a ways into it. Pretty cool. I put up on Teams, I made folders, so when you guys finish worksheets, you can just upload it into your folder. I have them in each of the channels. So like right now, you go into Unit 4, Formula Writing, go into that channel. It's like on the left-hand side. If it's the same for you guys, it is for me. And if you go under Files, you'll see where it says Submit Work. Just open that folder. You'll find your name. Click on that folder. Drop all your work into there, and that should make it pretty easy for you and I. So hopefully you guys can figure that out and you can start submitting work and whatnot. Okay, I think this has been long enough, so I'm going to go ahead and cut it off right here. I will make another video. The next one is going to be talking about polyatomic compounds, which is going to be another step in formula writing, but I think you guys will see it's kind of the same as what we've been doing already. So you guys take care, and I will talk to you soon. Bye-bye.